What's up, guys? Here we go. We are going to do Rolle's theorem now, please. So, oops, I thought I clicked that. We're going to our last mini lesson here on Rolle's theorem. So it says, if you have a function that is differentiable on the open interval, continuous on the closed interval, then there must be a value where f prime of c equals 0. Okay. Oh, wait. You can't even see what I'm writing. That's awesome. Okay. So Rolle's theorem says almost the exact same thing as mean value theorem. So these notes are going to be short. My function's differentiable on the open interval, continuous on the closed interval. Here's the one thing that's different right here. F of A and F of B have to be equal. That means that your Y value at the beginning is equal to your Y value at the end of the interval. Okay, so basically, in order to use Rolle's, differentiable, continuous, and your Y values have to be the same when you started as when you ended. If that is true, f prime is guaranteed to be 0. Let's talk about why. Take a look at this first graph. Oh, wait, hold on. I'll leave that on there. Okay, let's talk about why. So look at this first graph here. It says, for each graph below, apply Rolle's theorem on the interval and estimate the C value that would satisfy it. Okay, so from -2 to 2, -2 is here, 2 is here. Do you see that you have the same Y value? Equal Y values, check. Okay. Here's why this is true. Think about mean value theorem, we just did it. Okay, if you were to connect the average rate of change, you would notice that it's flat. That means the average rate of change when your Y values are the same is going to come out to be 0. So that means that I'm essentially looking for another 0 slope on that interval for them to be the same. So this is really still mean value theorem. The only difference is it's a specific case where your Y's are the same and your average rate of change is perfectly flat. So my C on this one would be, we'll say that's maybe like 0.5. Okay, take a look at the next one. Okay, I'm looking at my graph. I want to go from -1 to 2. Okay, well, -1 is here. 2 is here. So I notice again that my Y values are the same. That means that my average rate of change or my secant slope is perfectly flat, which is 0. Well, then I'm essentially looking for another place where I have a flat spot. Now, this is important. I have several flat spots here. I have one here, I have one here, and I have one here. However, your C has to be on the interval. So if I'm starting my graph at -1 and I'm stopping my graph at 2, then that means that I can only pick this one or this one. Okay, I cannot pick this one because it's not within the interval -1 to 2. So that cannot satisfy Rolle's theorem. Okay, Rolle's has to be on the interval just like mean value theorem. So I would have 2 options for that second graph, but not 3. Okay, even though it does have the right slope. So let's come ahead to number 7. It says, does Rolle's theorem apply for the thing? If yes, find the C. Let's do it. So first question I want to check is if my function is differentiable and continuous. Okay, well, it's a polynomial. So remember, any polynomial, like specifically this is a parabola, you just know that they're fine. Okay, so for part I, I'm going to put yes, it is continuous on 0 to 4, and it's differentiable on 0 to 4. Remember the difference. Continuous is closed. Differentiable is open. Step 2, I need to check and find that my y values are the same. If my y values are the same, I automatically know that I'm guaranteeing that there's a flat spot. So I'm going to find f of 0 and f of 4 and make sure that they're the same. If they are, then I can use Rolle's theorem. So 2 times 0 is 0, minus 4 times 0 plus 4. So 2 times 0 squared minus 4 times 0 plus 4, that's going to give me 4. Plugging in a 4 now, 2 times 4 squared minus 4 times 4 plus 4. That's going to be 4 squared is 16 times 2 is 32 minus 16. What? Did I plug that in right? 4 squared is 16 times 2 is 32 minus 16 plus 4. So that's 32 minus 20, which is 12. Okay. I don't know if I did this on purpose, but did my y values come out the same? No. If you get different y values, no Rolle's theorem for you. Okay, different y values cannot apply Rolle's theorem. Okay, Rolle's theorem is a special case that when my y values are the same, I know the derivative is going to be 0. But if they don't come out to be the same, then my derivative wouldn't have been 0, and I can't promise you that it's going to happen. Okay? All right, so when you're ready, go ahead and turn the page. Let's move on to number 7. Or wait, we just did number 7, number 8. Okay, one more page here. Okay, so Rolle's theorem, does it apply for the function x minus 2 plus 1 on the interval from 1 to 5? Let's check this function out. Okay, hopefully you know what, and actually I bet you know what it looks like without a graphing calculator. Okay, this is an absolute value. And absolute value functions are shaped like a, say it with me everybody, V, okay? So it's an absolute value. Also, we know that the minus 2 is going to shift it to the right 2. The plus 1 is going to shift it up 1. So if I were to sketch this graph here, I'd go over 2, up 1, and then I would sketch my V like that. Okay, it doesn't have to be perfect, but that's about what the graph would look like. Okay, so step 1 of Rolle's theorem is that I have to check to make sure that I have a continuous and a differentiable function. Okay, so it has to be continuous on 1 to 5. Well, it is. But it also needs to be differentiable. And what do you see here? Uh-oh. Okay, if it's a corner, not differentiable. So it's continuous on 1 to 5, but it is not differentiable at x equals 2 because there's a corner. And so there are 2 ways that you can mess up Rolle's theorem. The y values cannot be the same, or it cannot be both continuous and differentiable. So in this case, I am continuous, but I'm not differentiable. Therefore, MVT does not apply, not MVT, Rolle's. Rolle's theorem does not apply. Okay, and it doesn't apply because the basic criteria of the type of function is not ever met. And actually, let's talk about for a second, why not? If I pick 2 y values on this V that are the same, let's say I pick these 2. There's my perfect 0 slope. Here's the problem. I can't draw in a flat spot on a corner. Remember what we talked about. If it's a corner like this, how can I draw in a tangent line to it? This side, my tangent line has a positive slope. This side, my tangent line has a negative slope. Okay, but it never smooths out to give me that 0 transition. It just all of a sudden goes from this slope to this slope, and it never kind of like rounds out for me, okay, because it's a corner. All right, next one. Number 9, does Rolle's theorem apply for the function f of x equals cosine x plus 1 on the interval from 0 to pi? If yes, find the value of c. Think about the graph of cosine x plus 1. Cosine always starts at 1. So if I shift it up 1, it's going to start at 2. Here will be your little middle. And then cosine x is just going to go down, up, down, up. Okay, forever and ever for 100 years, as long as you want. Okay, that's what cosine x plus 1 looks like. Y equals cosine x plus 1. Okay, so look at it. Is it continuous? Yes. Is it differentiable? Yes. So let's just state that. Okay, so part I, it is continuous on 0 to pi. And I can see that it's differentiable on 0 to pi open. Okay, remember the difference, continuous, closed, differentiable, open. Step 2, I need to check that my y values are the same. So I want to check 0, which would be cosine of 0 plus 1. Well, cosine of 0 is 1. 1 plus 1 is 2. And then pi, which would be cosine of pi plus 1. Ooh, but pi is -1 plus 1, which is 0. So if I were to look at my graph on here, at 0, I'm at a height of 2, but at pi, I'm at a height of 0. So my y values, again, are not the same on this interval. So Rolle's does not apply. Okay. Okay, I started losing confidence that none of these are going to work, but it looks like the next one's going to work. Okay, so if I'm doing number 10, it's a Rolle's theorem question. We're doing it for pi to 3 pi. Okay, so let's redraw our little picture here. It's the same equation. Okay, cosine pi x plus 1. There's my sort of little middle guy. Starts at 2. Goes down, up, down, up. Okay, and if you remember anything from pre-cal, okay, this is pi. Then, hold on, 3 pi would be -1 again. What? This one doesn't work either. Okay, so look, here's your 0. Here's your pi. Here's your 2 pi, which would have been perfect. Let's just change it to a 2 pi. Otherwise, none of them ever come out the same. Okay, so we're changing it to a 2 pi. So now look, ooh, 0 and 2 pi. Finally, we have a problem where the y values are the same. Okay, which is what we've been wanting this whole time. So step 1, I can see that it's continuous. I can see that it's differentiable. Continuous on 0 to 2 pi closed. And differentiable on 0 to 2 pi open. Step 2, I can see from the graph that f of 0 is 1 and f of 2 pi is also 1. Now, if you're unsure how we know that, remember that on the unit circle, 0 and 2 pi are the exact same point. Okay? So 0 and 2 pi are the exact same point on the unit circle. So when you plug into cosine of 0 plus 1, you get 1 plus 1. That's the same as the cosine of 2 pi plus 1. You would get 1 plus 1, which would give you 2 again. Okay? So I would say, okay, well then finally, I have a continuous and differentiable function. My y values are the same. Then Rolle's guarantees, ... little confusion or a little conclusion here. Rolle's guarantees, it promises me that there is an X where f prime is equal to 0. And I can promise you that happens because my graph cannot turn from here to coming back to that exact same y value without having a flat spot, unless it has a corner, which I know it doesn't have because it's promised to be differentiable. Okay, then it says, if yes, find the value of c. Okay, well, I can just look at it from the graph. I know it's going to happen at pi. That's my flat, my 0 slope. So my c value for that one is going to be x equals pi. And then also confirm there are a bunch of flat spots, right? There's one here, there's one here, there's going to be another one here, right? But I need to have the one between my endpoints. So if I'm only considering from 0 to 2 pi, okay, then I wouldn't be able to choose any of the other guys. Also, I can't choose either one of these because remember, you're not allowed to pick the endpoints. So this would truly be your only C value for that one, okay? All right, last one here. I'm assuming you guys probably do not know what the graph of this guy looks like. So I'm just gonna graph it for you. But it's the cubic root. So I'm doing math 4 here. Okay, that's where your cubic root is of x squared. Okay, this is kind of an interesting graph. I'm gonna have to unzoom. But it's basically a cubic root graph if you flipped it all to be positive. So look at your graph. Doink. See, what does it have? Okay, it has a cusp, which means that I'm not going to be able to use mean value or Rolle's theorem on this one either. Okay, total tragedy, but that's okay. So sketch the graph here. Your graph goes down, and then it hits, and then it comes back up. Now, if I look in the table, okay, which I will show you here, -8 and 8 actually are, okay, -8, my y value is 4. And +8, my y value is also 4. Pretend this looks better. Okay, so the problem is not that my y values are not the same. I do have the same y value. Okay, the problem is that at this point right here, I don't have a true flat spot, I have a cusp. And so if you have a cusp, that means it's not differentiable on the interval from -8 to 8, which is a requirement for Rolle's theorem. So therefore, Rolle's does not apply, and Rolle's can't promise anything. Rolle's does not apply. So I can't promise that I'm going to have a flat spot. Also, I can see that I don't. Okay, but the reason that Rolle's theorem doesn't apply is because of that corner. Okay? All right. Great job. You're getting there.